Hey everyone, this is Morgan. We're talking about equilibrium constants, pages 5, 6, 7, etc. of the equilibrium lecture outline for Honors Chem. And today we're going to introduce the concept of an equilibrium constant. So what is it? I'm actually going to tell you 3 different descriptions of an equilibrium constant. The first thing is it's an algebraic expression. Meaning an equation. It's also a ratio, and it's also a number, a constant. So, these things do not exclude each other. An algebraic expression, you can plug numbers into it and get a ratio, and you can do the arithmetic and you can end up getting a number. But it's 3 different ways of describing it, depending upon what best suits our situation. So how do we write an equilibrium constant? K, capital, EQ. So K for constant, because originally this work came out of Germany, and constant is spelled with a K in the German language. KEQ equals. Now, if our chemical reaction is A of A plus B of B to form an equilibrium with C of C and D of D. That's a balanced chemical equation. The lowercase letters are our stoichiometric coefficients. KEQ is going to equal the concentration of C raised to the power of C times the concentration of D raised to the power of D divided by the concentration of A raised to the power of A, and the concentration of B raised to the power of B. The stoichiometric coefficients end up becoming exponents in this expression. So here you go. It's an algebraic expression, and it's the ratio of products to reactants. And we're going to say products over reactants an awful lot. Now, states of matter are going to be important. States of matter matter. Which ones are we going to exclude? We're going to exclude solids, and we're going to exclude liquids. Pure liquids, basically. When we're talking about this is going to be based on concentrations that change. And the concentration of a solid never changes. You can cut a rock in half, and you still have the same ratio of moles to liters, okay? Liquids, pure liquids, it's the same thing. Their concentration doesn't change. Now you're thinking, yeah, but what if I add water to it? Well, if you add water to it, it ceases to be a liquid and it becomes an aqueous solution, and that's something we will include. We include gases, and we include aqueous solutions. Now, water. Liquid water would not be included. Now, if you add water to it, what happens? Does it become more watery? No, I don't think so. It just is water, okay? But if you add water to another liquid, that turns it into an aqueous solution. Okay. Now, there are going to be a lot of varieties of equilibrium constants. I call this one KEQ, which is kind of the generic term. K, constant EQ equilibrium. We are going to work mostly with what is called Kc, which is based on concentrations. That's what this would be. Sometimes Kp, which is based upon pressures. And there are a lot of other Ks that we'll encounter as we go on in this. Now, the only difference between Kp and Kc is that Kp is based upon pressures. So for this same reaction, it would be the partial pressure of gas C to the C times the partial pressure of gas D to the D over the partial pressure of gas A to the A times the partial pressure of gas B to the B. It still takes that same format. It's just we do it with pressures rather than with concentrations. There are many types of Ks. They all end up being the same format. There's a K A for acids, a Kb for bases, a Kw for water, okay? There is a Ksp, which is a solubility product. There's a Kf, which is for formation reactions, all right? Lots and lots and lots of Ks.